The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Right, so the past few weeks we've been looking at double integrals in the plane, line integrals in the plane, and what we're going to do now, from now on, basically until the end of the term, will be very similar stuff, but in space. So we're going to learn how to do triple integrals in space, flux in space, work in space, divergence, curl, all that. So that means basically, if you were really on top of what we've been doing these past few weeks, then it will be just the same with one more coordinate. And you'll see there are some differences, but conceptually it's pretty similar. There are a few tricky things though. Now, that also means that if there's stuff that you're not sure about in the plane, then I encourage you to review the material that we've done over the past few weeks to make sure that everything in the plane is completely clear to you, because it will be much harder to understand stuff in space if things are still shaky in the plane. Okay, so anyway, the plan is we are going to basically go through the same stuff, but in space. So it shouldn't be surprising that we'll start today with triple integrals. Okay, so the way triple integrals work is if I give you a function of three variables, x, y, z, and I give you some region in space, so some solid, then I can take the integral over this region of our function f dv, where dv stands for the volume element. Okay, so what it means is we'll just take every single little piece of our solid, take the value of f there, multiply by the small volume of each little piece, and sum all these things together. And so this volume element here, well, for example, if you're doing the integral in rectangular coordinates, that will become dx, dy, dz, or any permutation of that, because of course we have lots of possible orders of integration to choose from. So rather than bore you with theory and all sorts of complicated things, let's just do examples. And you'll see, basically, if you understand how to set up iterated integrals in two variables, then you basically understand how to do them in three variables. You just have to be a bit more careful, and there's one more step. Okay, so let's take our first triple integral to be on the region. So of course, there's two different things, as always. There's the region of integration, and there's the function we're integrating. Now, the function we're integrating, well, it will come in handy when you actually try to evaluate the integral. But as you can see, probably, the new part is really how to set it up. So the function won't really matter that much for me. So in the examples I'll do today, the functions will be kind of silly. So for example, let's say that we want to look at the region between two paraboloids. One given by z equals x squared plus y squared. The other is z equals 4 minus x squared minus y squared. And so I haven't given you yet the function to integrate. Okay, this is not the function to integrate. This is what describes the region where I will integrate my function. And let's say that I just want to find the volume of this region, which is the triple integral of just 1 dv. Okay, similarly, remember when we tried to find the area of a region in the plane, we were just integrating 1 dA. Here we integrate 1 dv. That will give us the volume. Now, I know that you can imagine how to actually do this one as a double integral. But the goal of the game is to set up the triple integral. It's not to actually find the volume. So what does that look like? Well, z equals x squared plus y squared. That's one of our favorite paraboloids. That's something that looks like a parabola with its bottom at the origin that you spin about the z-axis. And z equals 4 minus x squared minus y squared. Well, that's also a paraboloid, but this one is pointing down. And when you take x equals y equals 0, you get z equals 4. So it starts at 4, and it goes down like that. Okay, so the solid that we'd like to consider is what's in between in here. So it has a curvy top, which is this downward paraboloid, a curvy bottom, which is the other paraboloid. And what about the sides? Where do you have any idea what we get here? Yeah, it's going to be a circle, because the entire picture is invariant by rotation around the z-axis. So, if you look at the picture, just say in the yz plane, you get this point and that point, and when you rotate everything around the z-axis, you will just get a circle here. Okay? So our goal is to find the volume of this thing, and there's lots of things I could do to simplify the calculation, or even not do it as a triple integral at all, but I want to actually set it up as a triple integral just to show how we do that. Okay, so the first thing we need to do is choose an order of integration. And here, well, I don't know if you can see it yet, but hopefully soon that will be intuitive to you. I claim that I would like to start by integrating first over z. What's the reason for that? Well, the reason is if I give you x and y, then you can find quickly what's the bottom and top values of z for that choice of x and y. Okay, so if I have x and y given, then I can find above that what is the bottom z and the top z corresponding to the vertical line above that point, the portion of it that's inside our solid. So somehow there's a bottom z and a top z. And so the top z is actually on the downward paraboloid, so it's 4 minus x squared minus y squared. The bottom value of z is x squared plus y squared. Okay, so if I want to start to set this up, I will write triple integral. And then, so let's say I'm going to do it dz first, and then say dy dx, for example. Doesn't really matter. So then for a given value of x and y, I claim z goes from the bottom surface. The bottom face is z equals x squared plus y squared. The top face is 4 minus x squared minus y squared. Okay? Is that okay with everyone? Yeah? Any questions so far? Yes? Why did I start with z? That's a very good question. So I could choose whatever order I want, but let's say I did x first. Then to find the inner integral bounds, I would need to say, okay, I've chosen values of, see, in the inner integral, you've fixed the two other variables, and you're just going to vary that one, and you need to find bounds for it. So if I integrate over x first, I have to answer the following question. Say I'm given values of y and z, what are the bounds for x? So that would mean I'm slicing my solid by lines that are parallel to the x-axis. And see, it's kind of hard to find what are the values of x at the front and at the back. I mean, it's possible, but it's easier to actually first look for z at the top and bottom. Yes?
Is there any way you pick dy dx or
dy dx or dx dy? No, it's completely at random. I mean, you can see x and y play symmetric roles. So, if you look at it, it's reasonably clear that z should be the easiest one to set up first. For what comes next, x, y, or y, x, it's the same. Yes?
Would it be easier to use cylindrical coordinates?
Yes, it will be easier to use cylindrical coordinates. I'll get to that just as soon as I'm done with this one. Okay. So let's continue a bit with that. And I mean, as you mentioned, actually, we don't actually want to do it with x, y in the end. In a few minutes, we'll actually switch to cylindrical coordinates. But for now, we don't even know what they are. So, okay. So I've done the inner integral by looking at, if I slice by vertical lines, what is the top, what is the bottom for a given value of x and y. So the bounds in the inner integral depend on both the middle and outer variables. Next, I need to figure out what values of x and y I will be interested in. And the answer for that is, well, the values of x and y that I want to look at are all those that are in the shade of my region. So in fact, to set up the middle and outer bounds, what I want to do is project my solid. So my solid looks like this kind of thing. And I don't really know how to call it. But what's interesting now is I want to look at the shadow that it casts in the xy plane. Okay, and of course, that shadow will just be the disk that's directly below this disk here that's separating the two halves of the solid. And so now I will want to integrate over. So I want to look at all the x and y, in the shadow. So now I'm left with actually something we've already done, namely setting up a double integral over x and y. So if it helps, here we don't strictly need it, but if it helps, it could be useful to actually draw a picture of this shadow in the xy plane. So here it would just look, again, like a disk, and set it up. Now, the question is, how do we find the size of this disk, the size of this shadow? Well, basically, we have to figure out where our two paraboloids intersect. Oops, there's nothing else. So. Okay, so one way how to find the shadow in the xy plane well, here actually we know the answer a priori, but even if we didn't, we could just say, well, our region lives wherever the bottom surface is below the top surface. Okay? So we want to look at things wherever the bottom value of z is less than the top value of z. I mean, less or less than equal, that's the same thing. So the bottom value of z is x squared plus y squared should be less than 4 minus x squared minus y squared. And if you solve for that, then you will get, well, so let's move these guys over here. You'll get 2x squared plus 2y squared less than 4. That becomes x squared plus y squared less than 2. So that means that's a disk of radius square root of 2. So we kind of knew in advance it was going to be a disk, but what we've learned now is that this radius is square root of 2. So if we really want to set it up using dy dx, like I started, then we can do it because we know, so for the middle integral now, we want to fix a value of x, and for that fixed value of x, we want to figure out the bounds for y. Well, the answer is y goes from here to here. What's here? Well, here, y is square root of 2 minus x squared. And here it's negative square root of 2 minus x squared. So y will go from negative square root of 2 minus x squared to positive square root. And then x will go from negative root 2 to root 2. Okay, if that's not completely clear to you, then I encourage you to go over how we set up double integrals again. Okay, does that make sense, kind of? Yeah.
So are we putting root 2 minus x squared just based on the idea that we still don't have another variable in there? Or like, how do we not know that that's exactly root 2? How do we know that the radius is root 2 like this?
Well, so when we set up, remember, we're setting up a double integral dy dx here. So when we do it dy dx, it means we slice this region of the plane by vertical line segments. So this middle guy would be what used to be the inner integral. So in the inner, remember, you fix the value of x and you ask yourself, what is the range of values of y in my region? So y goes from here to here, and what here and here are depends on the value of x. How? Well, we have to find the relation between x and y at these points. These points are on the circle of radius root 2. So if you want this circle, maybe I should have written, is x squared plus y squared equals 2. And if you solve for y given x, you get plus minus root of 2 minus x squared. Okay? Yes? Is there a way to compute this with symmetry? Well, certainly, yeah, this solid looks sufficiently symmetric that actually you could certainly, for example, if you don't want to do the whole disk, you could just do quarter disks and multiply by 4. You could even just look at the lower half of the solid and multiply then, by 2, so total by 8. So yeah, certainly there's lots of ways to make it slightly easier by using symmetry. Now, the most spectacular way to use symmetry here, of course, is to use that we have this rotation symmetry and switch actually, not do this guy in xy coordinates, but instead in polar coordinates. So the smarter thing to do would be to use polar coordinates instead of x and y. And of course, we want to keep z. I mean, we're very happy with z the way it is. But we'll just change x and y to r cos theta, r sin theta. Okay, because, well, let's see actually how we would evaluate this guy. So, well, actually, let's not. It's kind of boring. But so if you start, well, let me just point out one small thing here. Sorry, before I do that. So if you start computing the inner integral, okay. So let me not do that yet. Sorry. So if you try to compute the inner integral, you'll be integrating from x squared plus y squared to 4 minus x squared minus y squared dz. Well, that will integrate to z between these two bounds. So you will get 4 minus 2x squared minus 2y squared. Now, when you put that into the remaining ones, you'll get something that's probably not very pleasant of 4 minus 2x squared minus 2y squared dy dx. And here you see that to evaluate this, you'd switch to polar coordinates. Oh, by the way, so, if your initial instincts had been to, given that we just want the volume, you could also have found the volume just by doing a double integral of the height between the top and bottom. Well, you would just have gotten this, right? Because this is the height between top and bottom. So it's all the same. It doesn't really matter. But with this, of course, we'll be able to integrate all sorts of functions, not just one, over the solid. So we'll be able to do much more than just volumes. Okay, so let's see. How do we do it with polar coordinates instead? Well, so that would become, so let's see. So I want to keep dz, but then dx dy or dy dx would become r dr d theta. And if I try to set up the bounds, well, I probably shouldn't keep this x squared plus y squared around. But x squared plus y squared is easy in terms of r and theta. That's just r squared. Okay? I mean, in general, I could have something that depends also on theta. That's perfectly legitimate. But here, it simplifies. There's only r's. And this guy up here, 4 minus x squared minus y squared, becomes 4 minus r squared. And now the integral that we have to do over r and theta, well, we look again at the shadow. The shadow is still a disk of radius √2 that hasn't changed. And now we know how to set up this integral in polar coordinates. R goes from 0 to √2, and theta goes from 0 to 2 pi. Okay? And now it becomes actually easier to evaluate. Okay. So now we have actually a name for this because we're doing it in space. So these are called actually cylindrical coordinates. So in fact, you already knew about cylindrical coordinates, even if you didn't know the name. Okay, so the idea of cylindrical coordinates is that instead of x, y, and z, to locate a point in space, you will use 3 coordinates. One of them is basically how high it is above the xy plane. So that will be z. And then you will use polar coordinates for the projection of your point in the xy plane. So r will be the distance from the z-axis. And theta will be the angle from the x-axis counterclockwise. Okay, so the one thing to be careful about is because of a usual convention that we make the x-axis point toward us. Theta equals 0 is no longer to the right. Now theta equals 0 is to the front, and the angle is measured from the front counterclockwise. Okay, so, and of course, if you want to know how to convert between x, y, z and r theta z, well, the formulas are just the same as in usual polar coordinates. R cos theta, R sin theta, and z remains z. Okay, so why are these called cylindrical coordinates, by the way? Well, let's say that I give you the equation r equals a, where a is some constant. Say r equals 1, for example. So r equals 1 in 2D that used to be just a circle of radius 1. Now, well, in space, a single equation actually defines a surface, not just a curve anymore. And the set of points where r is a, well, that's all the points that are at distance a from the z-axis. So in fact, what you get this way is a cylinder of radius a, centered on the z-axis. Okay, so that's why they're called cylindrical coordinates. By the way, so now similarly, if you look at the equation, theta equals some given value, well, so that used to be just a ray from the origin. Now that becomes a vertical half plane. For example, if I set the value of theta and let r and z vary, well, r is always positive, but basically that means I'm taking a vertical plane that comes out in this direction. Okay, any questions about cylindrical coordinates? Yes? Yeah, so I'm saying when you fix theta, you get only a half plane, not a full plane. I mean, it goes all the way up and down, but it doesn't go back to the other side of the z-axis. Why? That's because r is always positive by convention. So, for example, here we say theta is 0. At the back, we say theta is pi. We don't say theta is 0 and r is negative. We say r is positive and theta is pi. It's a convention largely. But sticking with this convention really will help you to set up the integrals properly. I mean, otherwise, there's just too much risk for mistakes. Yes?
Going back to
Well, it depends. So the question is, if I were to use symmetry to do this one, would I multiply by 4 or by 2? Well, it depends on how much symmetry you're using. So I mean, no, it's your choice. You can multiply by 2, by 4, or by 8, depending on how much you cut it. So it depends on what symmetry you use. For example, if you use a symmetry between top and bottom, you'd say, well, the volume is twice the lower half. If you use the left and right half, you would say it's twice each half. If you cut it into 4 pieces, then, and so on. So it depends on, and again, you don't have to use the symmetry. It's just, if you don't think of using polar coordinates, then it can save you from doing, you can just start at 0 here and simplify things a tiny bit. But, okay. Oh, yes? So to define a vertical full plane, well, first of all, it depends on whether it passes through the z-axis or not. If it doesn't, then you'd have to remember how you do in polar coordinates. I mean, basically the answer is if you have a vertical plane, so it doesn't depend on z. The equation does not involve z. It only involves r and theta. And how it involves r and theta is exactly the same as when you do a line in polar coordinates in the plane. So if it's a line passing through the origin, you'd say, well, theta is either some value or the other one. If it's a line that doesn't pass through the origin, then it's more tricky, but hopefully you've seen how to do that. Okay. Let's move on a bit. So one thing to know, basically the important thing to remember is that the volume element in cylindrical coordinates, well, dx, dy, dz becomes r dr d theta dz. And that shouldn't be surprising because that's just, dx, dy becomes r dr d theta, and dz remains dz. So, the way to think about it, if you want, is that if you take a little piece of solid in space, so it has some height, delta z, and it has a base which has some area, delta A, then the small volume, delta V, is equal to the area of the base times the height. So now when you make the things infinitely small, you will get dV is dA times dZ, and you can use whichever formula you want for area in the xy plane. Okay. Now, in practice, you choose which order you integrate in. As you've probably seen, a favorite of mine is z first, because very often you'll know what the top and bottom of your solid look like, and then you will reduce to just something in the xy plane. But there might be situations where it's actually easier to start first with dx dy or r dr d theta, and then save dz for last. If you've seen how to, in single variable calculus, the disk and shell methods for finding volumes, that's exactly, the dilemma of, shells versus disks. One of them is you do z first, the other is you do z last. Okay. So what are things we can do now with triple integrals? Well, we can find the volume of solids by just integrating dV, and we've seen that. We can find the mass of a solid. Okay, so if we have a density, delta, which, remember, delta is basically the mass divided by the volume. Okay, so the small mass element, maybe I should have written that as dm, the mass element, is density times dV. So now this is the real physical density. If you're given a material, it will be, usually the density will be in grams per cubic meter or cubic inch or whatever. There's tons of different units, but so then the mass of your solid will be just the triple integral of density dV, because you just sum the mass of each little piece. And of course, if the density is 1, then it just becomes the volume. Okay. Now, it shouldn't be surprising to you that we can also do classics that we had seen in the plane, such as the average value of a function, the center of mass, and the moment of inertia. Okay, so the average value of a function f of xyz in the region R, that would be f bar would be 1 over the volume of the region times the triple integral of f dv. Or if we have a density and we want to take a weighted average, then we take 1 over the mass, where the mass is the triple integral of the density, times the triple integral of f density dv. So as particular cases, there's again the notion of center of mass of a solid. So that's the point that's somehow right in the middle of the solid. That's the point mass by which, that's the point at which you should put point mass so that it would be equivalent from the point of view of dealing with forces and translation effects. Of course, not for rotation, but so the center of mass of a solid is just given by taking the average values of x, y, and z. Okay, so it's the special case where so x bar is 1 over the mass times triple integral of x density dv. And same thing with y and z. And of course, very often you can use symmetry to not have to compute all three of them. For example, if you look at this solid that we had, well, I guess I've erased it now. But if you remember what it looked like, well, it was pretty obvious that the center of mass would be on the z-axis. So no need to waste time computing x bar and y bar. And in fact, you could also find z bar by symmetry between the top and bottom. I'll let you figure that out. Of course, symmetry only works, symmetry only works if the density is also symmetric. Right? If I had taken my guy to be heavier at the front than at the back, then it would no longer be true that x bar would be 0. Okay, next on the list is moment of inertia. And actually, in a way, moment of inertia in 3D is easier conceptually than in 2D. So why is that? Well, because now the various flavors that we had come together in a nice way. So the moment of inertia of an axis, with respect to an axis, would be again given by the triple integral of the distance to the axis squared times density times dv. And in particular, so we have our solid, and we might skewer it using any of the coordinate axes and then try to rotate it about one of the axes. So we have 3 different possibilities, of course, the x, y, or z axis. And so now rotating about the z axis actually corresponds to, when we were just doing things for flat objects in the xy plane, that corresponded to rotating about the origin. So secretly we were saying we were rotating about a point, but actually it was just rotating about the z-axis. Just I didn't want to introduce a z-coordinate that we didn't actually need at the time. So Okay, so moment of inertia about the z-axis. So what's the distance to the z-axis? Well, we've said that's exactly r. That's the cylindrical coordinate r. So the square of the distance is just r squared. Now, if you didn't want to do it in cylindrical coordinates, then, of course, r squared is just x squared plus y squared. Okay? Square of distance from the z-axis is just x squared plus y squared. Similarly, now, if you want the distance from the x-axis, well, that will be y squared plus z squared. Okay, try to convince yourselves on the picture, or else just argue by symmetry, if you change the positions of the axes. So moment of inertia about the x-axis is double integral of y squared plus z squared delta dv. And moment of inertia about the y-axis is the same thing, but now with x squared plus z squared. And so now if you try to apply these things for flat solids that are in the xy plane, so where there's no z to look at, well, you see these formulas become the old formulas that we had. But now, they all fit together in a more symmetric way. Any questions about that? No? Okay, so these are just formulas to remember. So let's do... No, okay. So let's do an example. Yeah. Was there a question that I missed? No? Okay. So let's find the moment of inertia about the z-axis of a solid cone between z equals a times r and z equals b. So just to convince you that it's a cone. So z equals a times r means the height is proportional to the distance from the z-axis. So let's look at what we get if we just do it in the plane of a blackboard. So if I go to the right here, r is just the distance from the z-axis. The height should be proportional with proportionality factor a. So that means, I take a line with slope a. If I'm on the left, well, it's the same story, except distance to the z-axis is still positive. So I get the symmetric thing. And in fact, it doesn't matter which vertical plane I do it in. This is the same, if I rotate about the z-axis. See, there's no theta in here. So it's the same in all directions. So I claim it's a cone where the slope of the rays is a. Okay? And z equals b, well, that just means we stop in a horizontal plane at height b. Okay, so that solid cone really just looks like this. That's our solid. Okay, so it has a flat top, flat circular top, and then it's pointing. And the point is at the tip of it is at the origin. So let's try to compute its moment of inertia about the z-axis. So that means, maybe this is like a top that you're going to spin, and it tells you how hard it is to actually spin that top. So actually, that's also useful if you're going to do mechanical engineering, because if you're trying to design gears and things like that that will rotate, you might want to know exactly how much effort you'll have to put to actually get them to spin, and whether you're actually going to have a strong enough engine or whatever to do it. Okay, so what's the moment of inertia of this guy? Well, that's the triple integral of, well, we have to choose x squared plus y squared or r squared. Let's see. I think I want to use cylindrical coordinates to do that, given the shape. So we'll use r squared. I might have the density, but let's say the density is 1. So I don't have density. I still have dv. Now, it will be my choice to choose, between doing the dz first or doing rdr d theta first. just to show you how it goes the other way around, let me do it RD theta dz this time. Okay, then you can decide on a case-by-case basis which one you like best. Okay, so if we do it in this direction, it means that in the inner and middle integrals, we fixed a value of z. And for that particular value of z, we'll be actually slicing our solid by a horizontal plane and looking at what we get. Okay? So what does that look like? Well, I fix a value of z, and I slice my solid by a horizontal plane. Well, I'm going to get a circle, certainly. What's the radius? Well, a disk, actually. What's the radius of that disk? Yeah, the radius of that disk should be z over a, because the equation of that cone, we say that z equals ar. If you flip it around, sorry, maybe I should switch to another blackboard. So the equation of a cone, it's z equals ar, or equivalently, r equals z over a. So for a given value of z, I will get, this guy will be a disk of radius z over a. Okay, so moment of inertia is going to be, well, I said r squared, r d theta dz. Now, so to set up the inner and middle integrals, I just set up a double integral over this disk of radius z over a. So it's easy. R goes from 0 to z over a. Theta goes from 0 to 2 pi. Okay? And then, well, if I set up the bounds for z, now it's my outer variable. So the question I have to ask is, what is the first slice, what is the last slice? So the bottommost value of z would be 0, and the topmost would be b. And so that's what I get. Okay? So exercise, it's not very hard. Try to set it up the other way around. With dz first and then rd theta. It's pretty much the same level of difficulty. I'm sure you can do both of them. So, and also if you want to practice calculations, you should end up getting pi b to the 5 over 10a to the 4, if I got it right. Okay, let me finish with one more example. I'm trying to give you plenty of practice because, in case you haven't noticed, Monday is a holiday, so you don't have a recitation on Monday, which is good, but it means that there will be lots of stuff to cover on Wednesday. So thank you. Okay, so third example. Let's say that I want to just set up a triple integral for the region where z is bigger than 1 minus y inside the unit ball centered at the origin. So the unit ball is just, well, it's the inside of the unit sphere. So its equation, if you want, would be x squared plus y squared plus z squared less than 1. Okay, so that's one thing you should remember. The equation of a sphere centered at the origin is x squared plus y squared plus z squared equals radius squared. And now we're going to take this plane, z equals 1 minus y. So if you think about it, it's parallel to the x-axis because there's no x in its coordinate, in its equation. At the origin, the height is 1, so it starts right here at 1, and it slopes down with y, with slope 1. Okay, so it's a plane that comes straight out here, and it intersects the sphere, so here and here, but also at other points in between. Actually, any idea what kind of shape this is? Well, it's an ellipse, but it's even more than that. It's also a circle. If you slice a sphere by a plane, you always get a circle. But of course, it's a slanted circle. So if you look at it in the xy plane, if you project it to the xy plane, then you'll get an ellipse. Okay, so we want to look at this guy in here. So how do we do that? Well, so maybe I should actually draw quickly a picture. So in the yz plane, it looks just like this, okay? But if I look at it from above in the xy plane, then its shadow, well, see, it will sit entirely where y is positive. So it sits entirely above here, and it goes through here and here. And in fact, when you project that slanted circle, now you will get an ellipse. And, well, I don't really know how to draw it well, but it should be maybe something like this. Okay, so now if you want to try to set up that double integral, that triple integral, well, so let's say we do it in rectangular coordinates because we are really evil. Well, so then the bottom surface, okay, so we do it with z first. So the bottom surface is the slanted plane. So the bottom value would be z equals 1 minus y. The top value is on the sphere. So the sphere corresponds to z equals square root of 1 minus x squared minus y squared. So you'd go from the plane to the sphere. And then to find the bounds for x and y, you have to figure out what the heck is this region here, okay? So what is this region? Well, we have to figure out for what values of x and y the plane is below the ellipse. So the condition is that, the plane is below the sphere, okay? So that's when the plane is below the sphere. That means 1 minus y is less than square root of 1 minus x squared minus y squared. So you have to somehow manipulate this to extract something simpler. Well, probably the only way to do it is to square both sides. 1 minus y squared should be less than 1 minus x squared minus y squared. And if you work hard enough, you'll find quite an ugly equation. But you can figure out what are then the bounds for x given y and then set up the integral. So just to give you a hint, the bounds on y will be 0 to 1. The bounds on x, well, I'm not sure you want to see them, but in case you do, it will be from negative square root of 2y minus 2y squared to square root of 2y minus 2y squared. So exercise, figure out how I got these by starting from that. Now, of course, if we just wanted the volume of this guy, we wouldn't do it this way. We'd use symmetry and actually we'd rotate the thing so that, our spherical cap was actually centered on the z-axis, because that would be a much easier way to set it up. But depending on what function we're integrating, we can't always do that.